Hi. The fact you're watching this video indicates to me that you, like me, are living in the digital age. Just in case you need it a little convincing, you'll recall that in the past, children read stories about poo. Today, children play with their Wii. My name's Cameron Rogers, and I'm a tertiary student at Avondale College, an institution in New South Wales, Australia, owned by the Seventh-day Adventist Church. I'm also teaching at Blue Hills College in Lismore. So what's the Wii all about? The Wii allows you to control your gaming environment through bodily gestures. Each remote, held by the gamer, has a multitude of motion sensors. It has an infrared camera out the front, which is used to track infrared objects. If you haven't checked out Johnny Lee's Wiimote whiteboard project, you'd ought to give it a look. Do a YouTube search for Wiimote whiteboard and you'll find multitudes of videos showing how you can use this $70 gadget to create an interactive whiteboard. But today I'm not interested in the infrared camera, I'm interested in the three-dimensional accelerometer. Each Wiimote contains an instrument that measures acceleration in each of the 3 dimensions. It takes a reading about 50 times a second, and its margin of error is very small. It's by far the most accurate accelerometer that's available to most high school budgets. Do a Google search for Wiimote logger, and you'll find this website here. The website contains links for downloading a Java application that can be run on Windows, on OS X and on Linux, and it contains all installation instructions. To connect the Wiimote, press buttons 1 and 2, and you can see that it's broadcasting for a nearby computer. Once the Wiimote has connected, it will look like this, with a single blue dot. You can see that I've got 2 separate Wiimotes connected. Wiimote logger will support multiple Wiimotes. So what does the data look like once you've captured it? The first column of the data here gives us the time elapsed. The second gives us the number of the Wiimote. This is your data for your X, for your Y, for your Z, and this is recording whether you've pressed button A and B. This data can of course be imported into any spreadsheet program and graphs can be drawn, but to save time I've written a small little applet in Mathematica that produces a live graph of the data being recorded from the Wiimote, and this should appear on the corner of your screen. Our first task is to identify which of the axes is the X, Y and Z axis and what units is the accelerometer calibrated to. To find this out, we can conduct a few simple experiments, and this is of course a very valuable problem-based learning task for students, to ask them to find out these things from the data they are recording. A simple experiment of leaving it on a tissue box will show that one of the axes is recording a unit of 1, a value of 1, and the others are recording 0. If I rotate the Wiimote through all the axes, you can see the data changing there on your screen. Okay, this leads us to think that the accelerometer is calibrated to units of 1 gravity, and it's recording forces. Obviously, when it's sitting on the desk, you would expect a value of 1 gravity, since that's the force with which the tissue box is pushing against the Wiimote. That's the normal force. And students who haven't met the normal force might be very interested in this experiment. It's a very ideal place to introduce it in the classroom. Okay, I'll grab the Wiimote, and supposing I shake it in this dimension, you can see the squiggles coming out. Axis, and if I do this, it should give you the Z-axis, and this, the Y-axis. Okay, those simple graphs give us enough working knowledge for us to use the Wiimote to record our data. If I take the Wiimote and place it in the bike that you can see behind me here, I'll place the Wiimote in the bicycle wheel, and you should notice some interesting data. I'm going to jam it inside the spokes. Okay, there it is. You can see the light flashing. When the Wiimote is on this side of the wheel. Obviously, we're recording a value of 1 gravity acting in this direction. It's along the x-axis. And when I flip the Wiimote down to the bottom, as you would expect, the value along the x-axis has switched sign. We're now having a value of 1 gravity acting in the opposite direction. Now, so as the bike wheel is spinning around, which it will be spinning around quite fast fairly soon, the value of contributed by gravity is going to oscillate plus or minus 1, plus or minus 1, plus or minus 1. However, anyone who's studied a bit of elementary physics will know that there has to be, for the Wiimote to travel in a circle, there has to be a thing we call the centripetal force. The centripetal force will always be acting towards the centre, in this direction. So let's see what happens as I spin up the bike wheel. Okay, you can see the data there appearing on your screen. And you can see that the mean position of the x value is actually changing. That's the contribution from the centripetal force. But you'll also notice that it's still oscillating plus or minus 1. That's the contribution from gravity. We're going to use this data to demonstrate that centripetal force is proportional to velocity squared. If I move the wheel 3 times as fast, you will need 9 times the centripetal force. Here we have the data we've just collected. We'll get rid of the green and the blue, the y and the z data, since that was not needed for our experiment. We really want to start at around 280 and finish just before 300. We're interested in this bit of data here. Okay, the data looks pretty good. It's a bit wobbly though. This is a good opportunity of teaching students techniques for reducing noise. A common one, of course, of which is the moving frame average. Let's specify, say, a moving frame average of width 6. And that smoothed our data down considerably. What we're interested in is these peak values. The distance on this axis, this is the time axis, between those peaks is the amount of time it took for the bicycle wheel to complete 1 full revolution. That's the period. That will tell us how fast the wheel was going. Here the wheel was obviously going very slow because it took a long time for it to do 1 revolution, whilst in this region it was obviously travelling quite quickly. The average position of our x values here will give the centripetal force, as we mentioned earlier. So it's these peaks we're looking at here. Hit the button, find maximum values, and I've programmed for Mathematica to find the time and force coordinates of these maximum points. Here we have a table. These are the time values and the force values corresponding to each of those maximum points. The period I found by subtracting adjacent time coordinates. So the difference in time between that one and that one was the amount of time it took to go around. The velocity I've calculated by doing 1 divided by the period. Period and velocity will obviously be inversely related. If it's going twice as fast, it will only take half the amount of time to complete 1 revolution. Velocity squared is reasonably self-explanatory. And here's the centripetal force. I calculated the centripetal force by averaging these 2 heights here to get a number, say, about in this region, and then subtracting 1, which brings it back to the mean value. If I plot the centripetal force against velocity, I don't end up with a very straight line relationship at all, especially when you consider that if I was to continue the line in this direction, it would obviously go through 0, 0, since if the Wiimote is not moving at all, I don't need a centripetal force. Let's try centripetal force plotted against velocity squared. And there we are, a beautiful straight line relationship that passes straight through 0, 0. I'm not sure if any member of the band Queen owns a Nintendo Wii. If they did, I guess it would have to be called the Royal Wii. But I do know what the band Queen would say if they could see all the marvellous ways in which this gadget can be used in the classroom. Surely there's nothing else to be said. We are the champions.